Senta, quando stai per iniziare vedo il countdown, giusto? Hello everyone, welcome back. I'm Fabio Calefato from the University of Bari. I will be the session chair for this session on papers concerning mining software repositories. We have a dense session, so I will, let's get started. We have 4 research papers and 3 of them have videos, and the last one will be a live presentation. So we can get started with the first video. It's on the paper Characterizing and Predicting Good First Issues. It will be presented by Yuekai Wang, who is here. Hello, Yuekai. Thanks for being here.
Okay. Hello, everyone. My name is Yuekai Huang. I'm from Institute of Software Chinese Academic of Science. Today, I will present our work characterizing and predicting good first issue. As we know, the continuous improvement of an open source software project depends on the developers who contributed to it. But many developers may not be able to participate in an open source software project for a long term. In order to keep the vitality of open source software, newcomers are highly needed. On the one hand, many developers also eagerly participate in open source software projects, driven by multiple factors such as better jobs or enjoyment. On the other hand, there are many barriers which may hinder newcomers from successful onboarding. Specifically, the newcomer often face the problem of not knowing where to start contributing to an open source software project, which prevent them from joining the open source community. To support the newcomers, many open source projects utilize the good first issue label to mark the issues that are suitable for newcomers to solve. However, manually labeling a good first issue is time and involved consuming given the large number of candidate issues. Therefore, we want to provide a thorough understanding of the characteristic of GFS and an automatic approach in GFS prediction. To achieve these goals, we mainly do 2 works based on the GFS from 10 popular open source software projects on GitHub. First work is to characterize what makes a GFI. Specifically, we first calculate 79 features which may exert a difference between GFIs and non-GFIs. These 79 features are mainly derived from 3 dimensions: clearness, issue description, complexity of change involved, and skill required. The first dimension used to characterize GFIs is clearness of issue description. Ideally, GFIs should have a clear issue description telling what the problem was and where to make the changes. And this is measured by 3 categories of features. The first feature category is report appearance. We assume the issue reporter's appearance will influence whether the issue have a clear descriptions. And this category contains 4 features. The second feature category is text richness. We assume the issues with rich texture descriptions is more likely to specify the errors to tackle and the change to make. And these categories contain 5 features. The third feature category is readability. The readability of the issue also reflects whether a newcomer can easily get the described problems and the required change. And these categories contains 36 features. The second dimension used to characterize GFIs is complexity of change involved. We think the scope of the involved changes of the issue should be also considered, and ideal GFIs should only touch a small part of code base, and it is measured by 2 categories of features. The first category is inference scope. We assume the that the potential influenceable of a GFIs should be as small as possible, and this category contains three features. And the second feature category is code complexity. We consider that the involved code of GFIs should be as less as possible, and these categories contain eight features. Another the features associated with code complexity can only be retrieved after the issue is closed. But in order to more comprehensively categorize GFIs and analyze its characteristic, we also extract these features. Where in the subsequent classifier establishment stage, we omit this category of features and use the other category of features to build the model. The third dimension to use to categorize GFIs is skill required. Ideally, GFIs should only require the limited skill so that the newcomers can manage to resolve them. And it is measured by two categories of features. The first feature category is issue types. We assume the type of the issue can potentially reflect how much inference is needed. And these categories contain eight features. And the second feature category is semantics. We assume the semantics involved in the textual descriptions of the issue indicate the required skills. And these categories contain 15 features. And after feature extraction, we categorize the GFIs with the hypothesis testing results about whether each of the above-mentioned feature exert a difference between GFIs and non-GFIs. Besides the hypothesis testing for signifying the significance of the test, we also calculate the effect size of the feature of the test. The table on the right shows the number of significant features and the number of features with not negligible effect size. We can see most of the investigated features exert a significant and substantial difference between GFS and non-GFS, and indicating they can be utilized for characterizing GFIs. Specifically, feature related to the semantic readability and text richness of the issue play a large contribution in GFI's characterization. The second work is to propose an automatically prediction approach based on the extract features. In detail, we compared four machine learning methods and selected the one with the high performance for GFI prediction, and then explore the contribution of features to distinguish GFIs, and also explore the influence of feature selection algorithm on performance. In predicting GFI's fate, we put forward three research questions. One is, are the proposal features good at predicting GFIs? In this question, we aim to evaluate to what extent the proposal feature can predict the GFIs. The second is, what is the contribution of each category of features in predicting GFIs? In this question, we examined the relative contribution of each category of features in predicting GFIs, which aim at understanding these features. The third is, can a reduced feature set achieve comparable performance compared to the full feature set? In this question, we examine the performance when using features selection algorithm which aim at providing actionable decision support for developers when choosing features in building GFI's prediction models. To answer research question one, we conduct the five-fold cross-validation on each project. Record each model's performance and treat the average values as the final performance of the project to avoid bias. We experiment with four common use machine learning algorithms to evaluate the GFI's prediction performance. And we use AOC to measure the performance of prediction models, and also adopt the matrix PFG kit, which is defined as the percentage of true GFIs identified by inspecting the top K% issues predicted by the models for fault-aware evaluation. As we can see, among the four types of machine learning-based models, random forest models can outperform others with a media is of 0.88 and the PFG20 is 0.77. And then we compare the best models as a random forest with state-of-the-art baselines and a random approach. We can see that the performance of our approach is significantly higher than the other two baselines, which further indicated the effectiveness of the proposal features in predicting GFIs. To answer research question 2, we use the same experimental setup as research question 1. We first experiment with each categories of features and obtain the performance of GFI's prediction and then conduct the improvements after removing each categories of features from the full feature set. We can see that with any categories of features, the GFI's prediction performance is significantly lower than the performance used the whole set of the feature. Furthermore, when removing each category of features, the prediction performance will decrease. To answer research question 3, we experiment with 3 common use feature selection algorithms. Based on previous hypothesis testing results, we additionally employed other 2 feature subset choice, SIGFED, which means all the significant features, and HSIGFED, which means all the features whose effect size is not negligible. We can see that compared with using all proposal features, no matter what feature selection algorithm is used, the performance will decline. Last, let me make a conclusion for our work. In this work, we propose 79 features from 7 categories of 3 dimensions to categorize the GFIs, and most of the features are significantly different between GFIs and non-GFIs. A feature related to the semantics, readability, and text richness of the issue play a large contribution in GFI's characterization. And our GFI's prediction approach can achieve a median AOC of 0.8 with the proposals features, which significantly outperform the state-of-the-art baseline. In general, all the proposal features are useful in predicting GFIs, and we recommend the practitioner utilize all the features in model building. That's the end of my presentation. Thank you for your listening.
Okay, thanks, Yuekai, for your interesting talk. Thank you. Please, people attending the question, you can type your questions. I will pick the most relevant ones, and we already have one here from Bill Franklin. I will show up. What are the semantic features? How to obtain semantic features? Thank you.
Thank you. It's a good question. And the semantic features is consisted of 2 parts. One is the topics number, and the second is base scores. And for the topics number, we use LDA models to capture the topic, and the base score we use the naive base 4-type naive base to calculate the possibility of the GF. And for the calculation, we split the training set as 2 subset and use 1 subset to training and predicting another subset. And for the test net, we use the whole training set, and to get the semantic features. And thank.
Okay, there's another one, the last one. We don't have much more time for more questions. From Ayushi Rastogi, how do distributions like Bernoulli indicate semantic features?
This in semantic features, we do the hypothesis, and almost all the features in the semantic feature categories is a significant difference, and with not negligible effect size. And Mm, uh, it means it's a substantial influence of these feature categories, and the details is on our papers. And thanks.
Okay, thank you, Yuekai. Our time is over for this presentation, and thanks again.
Thank you.
Let's move on to the next talk. The next paper is an empirical study on refactoring-inducing pull requests. It will be presented by Flavia Coelho. Hi, Flavia. Thanks for being here. I remove myself. We're just having a little issues with sharing the screen. Maybe virtualization shares, can we play the video instead? Okay, so we're going with the video, Flavia, okay?
Okay.
Okay. Please just a little patient. We're going to play the video in a minute. Yes, looks like there's no sound yet. Can we move on and maybe go back to Flavia while she managed to figure out the technical issues, and we move on to the third presentation. Ayushi, are you okay? Can you nod? Yes, Ayushi is okay. So there's a switch. We move on to the third paper, The Promises and Perils of Inferring Personality on GitHub, will be presented by Ayushi Rastogi. Thanks for being flexible, Ayushi. Yes, thank you. I'll leave you the floor.
I hope my screen is visible.
Yes, go ahead. It works.
Awesome. Hi, my name is Ayushi Rastogi. I'm an assistant professor at the University of Groningen. This talk is on the promises and perils of inferring personality on GitHub. It is a joint work with Frenk and Professor Andy Zaidman from TU Delft. What is personality? There are many definitions of personality in psychology, but in simple terms, it can be described as follows. This is me. How I think, feel, and act is an indicator and a reflection of my personality. To infer personality, one of the widely used model is OCEAN, also known as the Big Five or the five-factor model. Here, O stands for the openness to experience. It characterizes intellectual curiosity, imagination, and open mindedness. Likewise, the other four traits are defined. Conscientiousness is characterized by order, structure, persistence, and responsibility. Extroversion is linked to social engagement and assertiveness. Agreeableness reflects as concern of others' well-being and social harmony. And finally, neuroticism is characterized by the tendency to experience negative emotions. Now, how is personality measured? There are two widely known methods. The first is questionnaire, in which people answer a series of questions, responses to which indicate personality. This is what we know as a gold standard to measure personality. The other method uses signal. For example, using the text written by a person as a means to infer personality. Such tests are also referred to as psycholinguistic or text-based personality test. Talking about software engineering, there are many use cases to study personality, both individually and as team. For example, there are studies exploring contribution patterns, predict code review results, and even project success. Notably, most large-scale investigations apply psycholinguistic tests on SE communications data since they offer the flexibility to infer personality at scale, something that is hard to achieve via a questionnaire. Please note that the psycholinguistic tests in software engineering were trained on everyday use text. To this, SE communications introduce features that do not appear in a general text, for example, technical jargons. So, as studies exploring the role of personality in software engineering continues to grow, it is important to understand the promises and perils of inferring developer personality from SE communications data. Imagine a developer who writes text to discuss an issue. This text is fetched as an input to a psycholinguistic test, which then extracts indicators of personality. In this process, there are three sources of variability. Therefore, to assess the reliability of psycholinguistic test for SE, we study how the characteristics of developer, text, model, and their interactions can influence the inferred developer personality and how can we improve it. We conduct our analysis on GitHub. Before diving deep into the research questions, let me introduce to you the three state-of-the-art and practice psycholinguistic tests widely used in software engineering and justification for the choice. We chose two models from academia, Goldbeck and Yerkoni. Goldbeck is trained on small size data, for example tweets, while Yerkoni is trained on larger text, example essays and blogs. We also chose Personality Insights or PI from IBM. Unlike the two models proposed in academia, this model is trained on a wide range of text sources, constantly evolves, and is seen as a general purpose tool. Our first question investigates the influence of SE communications data on inferred personality. SE data is different from general conversations in two ways. One, it has technical words which have different meanings than everyday use. Example, cookie. And two, the use of GitHub flavored language. For example, text indicating markdown language. We identified 12 factors that can potentially influence inferred personality after looking them from four perspectives. First, pre-processing steps used in prior studies, example URLs, terms that can be incorrectly represented in software engineering. 3. Elements that raise privacy concerns, example mailing email addresses. And 4. Elements that can improve space or time efficiency, for example variance of space. To measure the influence of 12 pre-processing steps, we compute personality scores with and without the steps. If there exists difference in the inferred personality, we compare the scores to the ground truth inferred for a subsample of population via questionnaire. Here is a table from our study showing how removing a factor improved inferred personality scores and the percentage population influenced by a factor. Our advice for future studies inferring personality are 1. remove platform-specific features, for example, codes and code blocks, you will improve inferred personality scores. Also, we recommend removing some other factors such as white spaces and email addresses, which, while do not affect personality scores, improve the efficiency and lower privacy concerns otherwise. For the remaining questions, we applied the above pre-processing steps to minimize errors caused by them. Next, we explored if one model is better than other. We compared the personality scores inferred from the three models to each other and to the ground truth. Our analysis show that the three models are comparable with error margins ranging from 25 to 48%. The two exceptions are PI agreeableness and Goldbeck neuroticism, in which case the error margins were as high as 68% at 95% confidence interval, rendering the results meaningless. Our advice here is to choose any of the three models unless specific traits are relevant. Next, we ventured into text sizes of 100, 600, 1200, and 3000 words to gauge its influence on the inferential ability. Here too, we compared the personality scores inferred with different text sizes for a developer to see if increased text size indeed improved the inference. Our study shows that the inferential ability of PI and Yerkoni is optimal at 600 to 1200 words and 600 words for Goldbeck. Texts with less than 100 words give unreliable estimates, while beyond 3000 words, we expect no further improvements. Finally, to assess whether the English skills of a person influences the inferred personality, for a subset of developers, we solicit information on English proficiency. 1. We classified developers into those whose mother tongue is English or not. This was an objective way to infer English proficiency. Also, we classified developers based on their perceptions of fluency in English. We compared the differences in personality score for the developers based on their English proficiency. If the differences are high, English skills influence the inferred personality. Our study shows that fluency in English influences the openness to experience. Notably, many studies outside software engineering have shown that cultural background does influence openness to experience. We also found that PI and Yerkoni works best for non-fluent people, while Goldbeck for fluent people. So let's revisit the question. Do psycholinguistic tests reliably infer developer personality from software engineering data? Our study shows that psycholinguistic tests can be administered to infer developer personality with an average error rate of 41%. Since the error margins are high, care should be taken to draw conclusions from the inferred personality score. It also offers recommendation on how to improve inferred personality scores and introduces contextual factor, for example, English proficiency, which influences the inferred personality but cannot be controlled. Finally, we leave you with questions such as, should we infer personality in software engineering? And can psycholinguistic tests perform better on software engineering data? If you are interested in the answers to these and other related questions, read the full text using the QR code mentioned here. Should you have any questions, we can discuss it after the talk, or you can reach me via email. Thank you for listening.
Thank you, Ayushi, for an excellent talk. If you have questions, please type in. Meanwhile, I have one. As Ayushi know, we share the same interest and on the research topic. So one question would be, after reading your your paper and listening to your presentation. It's a two-part questions actually. So given the results that you have presented, so what happens to tools for personality detection, for automatic personality detection in software engineering? Do we use them or just rely on questionnaires, on more reliable solution? And if the answer is no, we don't abandon them, what is the next step in their development? What do we do now?
So I thank you for the question, Fabio. So first question was, should we use it in software engineering? And I would rather divide this question into two further sub-questions, like can we use and should we use? Of course, we can use, because as is also shown by many prior studies, that even with such a high error margins, these tests have been able to indicate about the contribution patterns, about the project success, so on and so forth. Now, the second question, like should we use? It's a little tricky one here. I mean, yes, there are numerous ways in which inferring personality can help us, can help software engineering in answering several questions, because I think this is quite well known that every phenomena that we study is socio plus technical, and looking into personality is an important aspect that can help us understand what's actually going in. But at the same time, one should be cautious in not taking these numbers very seriously too hard. For example, one should not use them for hiring, because the challenge here is what these numbers are. And as I've already said in the paper, that the average error rate is like 41%. So just because it says something as your inferred personality, it may or may not be the case. And an even more complicated issue that we figured out while we were doing this study was that people, for example, with bipolar disorder, the inferred personality for them may not actually match their real one, because personality that we capture is just a snapshot of time, and their behaviors keep on changing. So there are a lot of such implications, and one should be cautious in where they are using and for what purpose.
Okay, quickly, the second part, yeah, what will you do to improve one tool right now? If you have to pick something, just one, how do we improve tools?
Well, I don't think we can do anything more better in the psycholinguistic test, but I do feel that there is a hope for machine learning based solutions, especially if something can capture the semantics and not just the syntactic features as we used in the study. So to just explain, if we can express or differentiate a natural language conversation from an SE specific terminology, I think those solutions can render better results for sure.
Quickly, I think you can answer this question. How did you determine grounded truth of personality, and what were the privacy concerns?
Okay, so for the ground truth, as I also introduced previously, the only method lies is questionnaire. So we conducted a survey. We sent a list of questions to developers also from GitHub. And of course, we told them that, see, this is how we are going to use the results of the study, and they can back out of it at any point of time. And we also told them, as a part of the privacy concern and in compliance with GDPR, what their rights are, how this data will be kept and stored. So that was our means of inferring the ground truth for the study.
Okay, thank you, Ayushi. Super interesting work and excellent presentation. Thank you again.
Thank you, Fabio.
Let's move on. Next presenter is Simone Romano. He will be presenting their study, an exploratory study on dead methods in open source Java desktop application. Thank you, Simone.
Thank you, Fabio, for this introduction. I am presenting an exploratory study on dead methods in open source Java desktop applications, as you said, and I would like to introduce the other authors of the paper I'm presenting, namely Danilo Caivano, Pietro and Giuseppe Scagnino. This presentation is about dead code. Dead code is code smell. It is also known as unused code, unreachable code, or lava flow. Dead code can refer to code blocks, fields, methods, or even classes and files that are unused. In our study, we focused on a kind of dead code, namely on dead methods. In other words, we focused our attention on unused methods. Dead code and thus dead methods are introduced into a code base because developers think to use that code in the future. However, predicting the future is difficult and that code is harmful. In particular, empirical evidence has shown that dead code hinders source code comprehensibility and it also negatively impacts source code maintainability. In our study, we wanted to increase our body of knowledge on dead code and in particular on dead methods. And so our study goal was to understand the spread and evolution of dead methods in open source Java desktop applications. In line with our study goal, we formulated 5 research questions, one about the spread of dead methods in open source Java desktop applications, and 4 research questions about the evolution of dead methods. However, here, for time reasons, I can just show you the results about 3 research questions. I have chosen the research questions for which, in my opinion, we got the most interesting results. To pursue our study goal and thus to answer our research questions, we conducted an exploratory study. We analyzed the commit histories of 13 open source Java desktop applications whose software projects were hosted on GitHub. More in detail, in each commit of each of the studied applications, we automatically detected which methods were dead and which not by using a supporting tool, namely Dead Code Finder. Our first research question was, are dead methods spread in open source Java desktop applications? We can postulate that the higher the number of dead methods in a given application, the higher the likelihood for a developer to bump into a dead method during a maintenance task, so the higher the probability to experience the negative effects of dead code in terms of worsened source code comprehensibility and maintainability. To answer this research question, we considered the relative number of dead methods in a commit. Here we can see some descriptive statistics about the relative number of dead methods in a commit for each of the studied application. And we can notice that only in one case, on JDM, we have a minimum equal to 0%. So meaning that only in JDM, we have a commit without any dead method. In all the other cases, we have at least a commit with at least a dead method. Moreover, if we look at the median value, we can notice that in 10 applications out of 13, the relative number of dead methods in a commit is greater than 10%. So we can conclude that dead methods are spread in open source Java desktop applications. With our second research question, we focused on the evolution of the methods. And the second research question is, how long do the methods survive in open source Java desktop application? Here we can postulate that the older that method, the more difficult it is its future use or reuse, because it should not be updated with the rest of the system, since it was written at the time the system was different. To answer this research question, we considered the median survival time in terms of commits. We computed the median survival time by using a survival analysis method, namely the Kaplan-Meier one. Here we can see the results about the second research question. And in the second column, we can see the number of commits for each of the studied applications, while in the last two columns, we can see the median survival time in terms of commits, as well as the confidence interval. We can notice that on 8 applications out of 13, we have a median survival time in terms of commit that is greater than 10 commits. This number is not so small if we consider the total number of commits for each application. Moreover, we can see that in 2 cases, on Edueter and Bitbox, we could not compute the median survival time because we did not have enough data. So we can conclude that the methods survive for a long time in open source Java desktop applications. The last research question I'm showing you is the fourth of our paper. And this research question is, do developers survive dead methods in open source Java desktop applications? So with this research question, we wanted to understand whether dead methods are actually used in the future. To answer this research question, we considered the relative number of dead methods in the commit history that are revived. Here we can see the results, and we can notice that on 8 applications out of 13, the percentage of revived dead method is lower than 15%. And also the median value is low, and it is lower than 15%. So we can conclude that dead methods are rarely revived in open source Java desktop applications. Summing up, we know that dead code and thus dead methods are harmful. Moreover, we have observed that dead methods are spread, survive for a long time, and are rarely revived in open source Java desktop applications. So we can distill a main message for developers, and this main message is actually borrowed from Robert Martin. This message says, when you find that code, do the right thing, give it a decent burial, delete it from the system. This is my last slide, and I hope you liked the presentation. And if you want to know much more about that code and you want to know something about the results of the other 2 research questions, please have a look to our paper. That's all.
Thank you, Simone. Thanks also for being perfectly on time. There is one question. It's a quick one. You can answer quickly. The answer is yes.
Yes, the tool is available online. You can find any reference in our paper.
Okay. Meanwhile, I don't see other questions. So I think, Simone, you can maybe use this time to maybe give us a bit of insight about the other two research questions you didn't have time to cover due to time limitation. I think it's 3 and 5. Can you tell us about the findings?
Yeah, the third research question was about the dead methods that were removed. And we observed that in some applications, developers removed that method with a good amount. I mean, we have more than 40% of that method removed, while in other not. And we also observed that, however, the percentage of removed methods was almost always higher than the percentage of dead methods that are instead revived. This is another of our results. And then we observed that in most of the cases, dead methods born as dead rather than becoming dead later.
Okay. Okay, thank you, Simone. I don't see other questions in the chat, so I think we can all thank you again for an interesting talk. And we can go back to the second presentation that we have delayed by Flavia Coelho, an empirical study on refactoring-inducing pull request. Let's see if the screen share works now, hopefully, fingers crossed. And okay.
Hello everyone, I'm Flavia. Today I'm going to talk about refactoring-inducing pull requests. Everything begins with modern code review, a process driven by reviewing code changes and available in platforms such as GitHub, for example. As you can see in the figure, an author can submit code changes through commits like commits 1 to 3 in the figure. These commits are organized into multiple lines of development named branches, such as Apache Master and Zaidman command out recovery. After opening a pull request, a reviewer can inspect the code changes, providing review comments about issues or suggestions. In this context, we realize that the result of that reviewing discussions may comprise refactorings in commits 4 to 9. So, our main objective is to get an in-depth understanding of refactoring-inducing pull requests, but what are they? Now, I'd like to draw your attention to our definition for refactoring-inducing pull requests. For us, a pull request is a refactoring-inducing if refactorings are performed in subsequent commits after the initial commit as a result of the reviewing process or spontaneous improvements by the pull request author. To clarify, this figure shows a refactoring-inducing pull request consisting of 3 initial commits, commits 1 to 3, and 6 subsequent commits performed after the pull request openness, that is, commits 4 to 9. In 3 subsequent commits, you can see refactorings. Therefore, our study explores differences and similarities between pull requests based on the refactorings performed in commits after the initial ones. It's worth mentioning that there's a novel definition because previous research on refactorings, code review, and pull-based development have considered refactorings performed as from the second commit. Now, I'd like to move on to our study design. These research questions drive our investigation. Firstly, we explored the presence of refactoring-inducing pull requests. Then, we investigated quantitative aspects related to code reviewing to find out similarities and difference between pull requests based on the presence of refactorings. Lastly, we manually examined review comments and discussions of a sample of refactoring-inducing pull requests to validate the occurrence of refactorings induced by code reviewing. So let's start by the first step. First of all, we mined merged pull requests from Apache repositories and GitHub. We considered merged pull requests because we could analyze completed review process. In step 2, we ran a state-of-the-art tool for many refactorings performed in merged pull requests from step 1. At that point, we also checked the authority date of the commits against the opening date of their pull requests to identify initial and subsequent commits. After this step, we got an answer to our first research question, that is, how common are refactoring-inducing pull requests? In step 3, we collected attributes related to code reviewing for all merged pull requests, having at least one review. For choose the attributes, we performed a compilation of 18 works. I'd like to show these attributes. In the table, you can see a few attributes, such as the number of added and deleted line that form the code churn, and the creation date and merge date of a pull request, which the difference indicates the time to merge a pull request. So we began to think about a strategy to better investigate our sample. Then unsupervised machine learning emerged from our journey. As a result, we found association learning that identifies a natural structures named association rules derived from the characteristics of data. For example, pull requests having a high number of review comments tend to have a high number of reviewers. So, association learning supported us in the formulation of more accurate hypotheses on differences and similarities between refactoring-inducing and non-refactoring-inducing pull requests. In this step, firstly, we performed a statistical testing of hypotheses formulated in step 4. After this analysis, we got the answer to our second research question, that is, how do refactoring-inducing pull requests compare to non-refactoring-inducing pull requests? Then, we carried out a manual inspection of a sample of refactoring-inducing pull requests in order to answer our third research question. Is refactoring induced by code reviews? For that, 3 developers intending to mitigate researcher bias during 30 days manually examined, reviewed discussions, and validated the mined refactoring as a subsample of refactoring-inducing pull requests. These are the samples considering data analysis. Our quantitative analysis considered data from a lot of merged pull requests from 84 distinct Apache repositories, while our manual inspection was performed on a stratified sample of almost 300 pull requests. Now, I'd like to focus on our findings. So, how common are refactoring-inducing pull requests? We found more than 30% of refactoring-inducing pull requests in our sample. In the figure, you can see the histogram of refactorings is positively skewed. Even presenting outliers, a low number of refactorings is quite frequent. These results reveal significant refactoring activity induced in pull requests. For us, this is a motivating result. Moving on the next research question, we investigated how do refactoring-inducing compare non-refactoring-inducing pull requests. We found that refactoring-inducing pull requests comprise significantly more code churn, file changes, subsequent commits, review comments and discussion, and time to merge than non-refactoring-inducing pull requests. This is an expected result in terms of code churn, since previous research also found quite similar results. For instance, we confirm that refactoring code has significantly higher size-related metrics, and that more file chains comprise more change during code review. Therefore, we expected that reviewing refactoring-inducing pull requests might require more subsequent changes, in turn denoted by subsequent commits, in contrast to non-refactoring-inducing pull requests. Moreover, when considering refactoring how improvements to the code, our finds also reinforce the recent research that found that the most changes during code review are driven by reviewing comments and discussion. Our findings also reinforce the influence of refactorings on time to merge, concluding that time for reviewing and performing refactorings both impact the time to merge. About the number of reviewers, we found no statistical evidence that is related to refactor-inducing. So this topic really needs further investigation. When investigating if refactor-inducing by code review, we found almost 60% of refactor-inducing pull requests in which at least one refactoring was induced by review comments. Specifically, we found that rename and change types in the instance are the most induced by code review. By the way, readability is a common motivation cited by reviewers when suggesting rename refactorings. In practice, the main implications of our study are a few actionable directions for researchers, practitioners, and to builders. First, we recommend that future study design on modern code review with pull requests can make a distinction between refactoring-inducing and non-refactoring-inducing pull requests, or at least consider the different characteristics when sampling pull requests. For pull request managers, for instance, we suggest that they can invite more reviewers when a pull request becomes refactor-inducing to share the expected increase in review workload and the knowledge of design changes to more team members. For two builders, we suggest the development of, for example, bots to recommend reviewers based on some criteria to help the pull request managers when inviting additional reviewers. To finish, thanks for your attention. I'd be happy to answer any questions.
Okay, thanks, Flavia. We finally managed to listen to your interesting talk. At least it was worth the wait. We have a question already from Carlos Eduardo here. I will read it out. What was the criteria to choose the Apache ecosystem as the dataset?
Hello, everyone. Apache is a significant project. I have significant project in the open source world. Specifically, we found Apache as a ecosystem that really use GitHub requests a lot. So we could perform an investigation of this one in considering a lot of contributions, a lot of projects, distinct repositories. So we have a many of settings to investigate.
Okay, thank you. I have another one. So I saw you basically applied a frequent pattern algorithm to understand, the associations of actions in the dataset. So I was wondering if you ever considered looking into the evolution of this algorithm, like for sequential pattern mining. So in a way that you can understand if refactoring action A is followed by B and C more often, instead of just looking at association based on frequencies. I mean, you mentioned the FP growth algorithm, and I know that the FP algorithm has an evolution that looks into the sequences of action as well. So maybe you didn't have you haven't considered that.
Oh, great.
No, okay. Okay, thank you. There's last questions, and then we have to close. Is Refactory Miner available, or can it be integrated to a code repository pipeline? Thank you, Peter.
So, Peter, Refactoring Miner is really available. We can change. We can find this tool at GitHub. It can be integrated to the code repository, and everything is really available for study. It's a great tool for help us to support us in the investigation of refactoring during code evolution.
Okay. Okay, thank you, Flavia. Thanks again. So your talk closes this session. We have a short break, and we will resume at 3:30 Central European Time with the second session on mining software repository and energy consumption with the last two research papers. So I will see you again after the short break. Thank you.